Okay, let's talk about the electric potential energy of a finite charge distribution. So let's say I have right now an empty universe and I put a single charge in there, say Q1. Well, I have no electric field other than what this guy is creating, so I'm free to move this guy around all I want. His own electric field won't fight him. So the energy to move him around or to place him wherever I want is zero. He's free. I can move him around, I can place him for free. Now let's say I bring in a second charge. So let's say we add in a Q2. So I've got, say, charge 1 that was free, and I bring in from infinity charge 2, and I move him that close to charge 1, some distance r away from charge 1. Well, that's going to cause me work. It's going to cost me work. I'm going to have to squish these guys together. Well, then that energy will be K Q1 Q2 over R. That's how much energy it cost me to bring them together. That's how much energy is bound up in the electric field. If I keep bringing in more charges, it's going to cost me more energy. I'm going to have to do more work to bring in more. So let's say I add in some third charge. Well, both of these guys that are already there are going to try to fight me bringing in this third charge. So say I, for example, tried to arrange this triangle. And I don't know, now we're going to need multiple R's. Say this is R1 to 2, R1 to 3, and R2 to 3. And here are my three charges in this triangle. Well, the new energy I'm going to have, the new work I'm going to have to do, the energy bound up in the electric field will be whatever energy I already had, plus this new energy to get this guy in, and both of these guys that I'm holding still, I've glued these two down, the energy to get this new guy in. So I'm going to have to add to what I already had, K Q1 Q3 over their distance, R 1 to 3, plus K Q2 to 3, Q2 Q3 over their distance. So when you're bringing in a whole bunch of charges, the total energy, U total, will be the sum over all possible pairs, I and j, of qi, qj, over the distance, I can't forget my k there, over their distance. So when you're adding up a whole bunch of charges, my suggestion to you is start small. Start with one charge, bring in one, bring in the next one, bring in the next one. And every time you bring one in, you need to find the energy between that charge and everyone that already existed. This is a sum over all possible pairs of charges. Okay, so say for example, we wanted to work a problem where we built 4 charges into a square. We wanted to find the total electric potential energy to do that. So we won't do this with numbers, we'll just do this conceptually. Q3 and Q4. Okay, and we have all these different distances. If this is a square, then obviously all the sides would be the same. But let's say just for simplicity or for completeness, all the distances are not all the same. So here we have the distance between 1 and 2, the distance 1 and 3, distance 3 and 4, and distance 2 and 4. And I wanted to figure out how much energy is required to squish these charges together. Then you always start with one of them and that guy's free. So Q1 is free. You can bring him in, you can move him around, you can do whatever you want with him. Nobody's fighting him. So in my mind, in my universe right now, I have one single charge. Then we add in one charge at a time, and everybody that's already there will fight that new guy. So add in Q2. So my universe right now will just be two charges separated by this distance, R12. That's the distance between them. Then that amount of energy is K, Q1, Q2 over that distance. Add in a third charge. So add in Q3. So the two guys that are already sitting there are both going to fight him coming in. So I've got this distance here, R13. I'm going to need to use Pythagorean to find this distance across this diagonal, R23. See, I'm going to need that distance between Q2 and Q3. So the additional energy to bring this guy in will be K, Q1, Q3 over their distance plus K, Q2, Q3 over their distance. And again, I would need Pythagorean to find that distance. That's the distance across my rectangle or square or whatever it is. Then if I bring in Q4, I've already got three charges in there. Q1, Q2, and Q3. Now I've glued those three down. They're stuck in place. If they weren't, they would fly apart on their own even before I try to bring this other guy in. So I've brought the first three together and I've glued them down. They can't move. Now I'm slowly bringing in Q4. How much additional energy would that require? Well, that would be Q1 to Q4, so I would need to find this distance. K, Q1, Q4 over the distance from 1 to 4. Plus everybody that's already there, 2 and 4, over their distance, the distance between 2 and 4. Plus K, Q3, and Q4 over their distance. That would be this side down here. So the total energy for getting all four of these charges together, I would have to add up. Q1 was free. There's the first. Plus these two. That was to get Q2 in. Two more to get Q3 in, plus three more to get Q4 in. I'd have to add up 1, 2, 3, 4, 5, 6 different energies. And that's the best way to approach these. Don't try to just write down all of them. Do it step by step. Bring in one charge at a time and find the energy that each charge that's already there contributes to bringing in that new charge.